Hello and welcome to Math 95 Online. This video lesson is section 6.6 out of the Math 95 book for Columbia Gorge Community College. This section is titled Complex Numbers, and it's a pretty exciting lesson because you get to learn a whole new set of numbers called the complex numbers that we've just sort of avoided and said that they're not real numbers so far. So today's a pretty big day, and I have some exciting pictures to show you of just the usefulness and the beauty of complex numbers, which is kind of exciting. You might come away from today thinking my instructor is really nerdy, but I'm okay with that. Anyway, so complex numbers. So first of all, let's sort of motivate why we need to learn about complex numbers. So if you get something like this, right, the square root of negative 16. So far we've just said not a real number, right? Well, what it is, not a real number. What it is it's a complex number. And what we do with complex numbers is just like the unit 1 is how we count with real numbers. The standard unit that we have is the square root of negative 1. We call this I. And so all complex numbers are written in terms of I. So if we were to simplify this guy in terms of I, we could say, well, this is the same thing as negative 1 times 16. And then we use our little properties and say, well, this is the square root of negative 1 times the square root of 16. And our new definition that the square root of negative 1 is I. So then we can say, well, this is I. Square root of 16 is 4, which is 4I, which is a complex number. So we will no longer just say we can't take the square root of negative 16. We'll say it's a complex number, and we'll be able to name it, which is great. So we really want to remember that I is the square root of negative 1, and then what happens if we square both sides? So I squared, and when we have negative 1 squared, then we get that I squared is negative 1, which is important to note. So these two things are quite important. Now, complex numbers are always written in a particular form. Complex numbers. So they're always written in a plus bi, where this I is the square root of negative 1 that we were just talking about. So it's always written like that. And let's see. Well, first I should tell you that A and B are real numbers. Okay, A and B are real numbers. I is the square root of negative 1. This is called the really fancy, the real part. And this is called the imaginary part. Okay, the real part and the imaginary part. And then we like to define, just like we graph equations in the real number system, we have the x and y axis. We can graph complex numbers. And what we do is we have the same sort of looking coordinate system, but we call this guy the real axis. And we call this guy the imaginary axis. Okay? So if we want to graph 3 plus 2i, then what we do is we go 3, the real part is 3, right? This is the real part. So we go over 3, and then this is the imaginary part. So we go over 3 and up 2. and that is the graph of the imaginary number 3 plus 2i. Now that we've spoken a little bit about complex numbers and what they are, granted not very much, I want to show you something really amazing about these complex numbers. In, I believe it was 1960, but I could be wrong. 1960, there's a guy named Mandelbrot, and he decided to put his computer to work on these complex numbers, and he defined these are called recursion formulas. That's something like this, where z is a complex number, and actually we have these little double-headed arrows. I'll tell you what that's about. And what he did was he said, okay, I want to take a number that's on that graph I was just showing you. Where is that? The previous page. So each little dot on this graph represents a complex number, right? And so what he wanted to do is he wanted to take each spot on the graph and he wanted to put it into, have his computer put that into to an equation like this, okay? And see what pops out, and then he would keep doing that over and over and over again, and if the number rushed off to infinity, he would color it a certain color, and if it went to 0, he'd color a different color, and if it went with different speeds, grew with different speeds, he'd color a different color, and see what he came up with. And so let me explain this a little bit more, and I'll show you what he means by recursion formula. But let's let z start out just being a real number, like 2. Okay? So then what you do is you do 2 squared plus 1. 2 squared is 4. 4 plus 1 is 5, right? Then he would take the number 5, the output, and he'd put it back in. So then you'd do 5 squared plus 1, which 5 squared is 25 plus 1 is 26. And then he'd take that number and put it back in. 26 squared plus 1, and so on and so forth. And you can see that this number is getting very big very fast, and so then he, let's say this one went to infinity at a certain speed, and he'd color it that color, and then he would try a different number. And it turns out that with complex numbers in the form a plus bi, you get these gorgeous pictures, okay? So I'm going to show you, let's see, there's this website called coolmath.com, and they have these pictures of fractals. These things are called fractals. So this is one of them, and this is one of my favorites. I love this one. And what's awesome, so this whole black area, I'm guessing that is the color for 0. So where all these numbers in here, where they go to 0. But what's amazing about these fractals is that you can zoom in infinitely, and you still get this really, even with increasing detail, picture of and this pattern that you can see. So actually, this website lets you, if you go to a fractal generator. So here's one of them. And then what it kind of does is it allows you to like zoom in on these different parts, and you can just keep zooming in, and you can just see this incredible detail that just goes on forever. Oh, that's really pretty. I love green. Anyway, it just keeps going and going and going, and you can kind of focus in on one area if you want. Isn't that incredible? Oh, I don't know what just happened. The computer has issues at some point and then just like stops working. But that doesn't mean that the fractal had the issue. It's just the computer. So anyway, that's pretty fun. So you can Google fractals and you can just find a bunch of them if you want to take a look around. I really like this one. Let's look at another one. That's kind of weird. So each of these has a particular, just like I was showing you, that z equals z squared plus 1. These have a particular formula like that. This one kind of reminds me of Dr. Seuss or something. Anyway, you can play around with those and see what you can find. Okay, back to complex numbers. Okay, so one thing that you're going to be asked to do in this chapter is to add and subtract. I want to go back to black. So let's say that you have 2 plus 3i, that's a complex number, plus 4 minus 7i. Okay? And you want to add those together. You can kind of treat the I as if it were like a variable x, except for you know that it has the value square root of -1. So what you're going to do is you're just going to add like terms. So the 2 and the 4 are like, and it's 2 plus 4, so that's 6. And the 3i plus -7i is -4i. So there you have it. It's in standard form. We always want to write it in the form a plus bi. This is standard form. And the book will always ask you to write it in standard form. Okay, what if we had 2 plus 5i minus -3 minus 2i. Okay, so you have to be careful of this minus, and you might want to distribute it first. So 2 minus -2 plus 3 is 5, and 5 minus a -2i, 5 plus 2i, so that's plus 7i. Not too bad, huh? Then we do multiplication, which you're just going to FOIL. So 4 minus 3i times 2 plus 5i. Okay, so 4 times 2 is 8. 4 times 5i, that's just going to be 20i. -3i times 2 is -6i. And then minus 15i squared. You combine like terms, you get 8 plus 14i minus 15i squared. And then recall that I squared equals -1, right? Since I is the square root of -1, if you square both sides, then you get I squared is -1. So this becomes 8 plus 14i plus 15, or 23 plus 14i. Anytime you have an I squared, you automatically want to substitute -1 for that. You should never have anything any higher power than a 1. You can have just an I left, but anything other than that you want to simplify further. Okay, so that is multiplying, and then we have dividing, which kind of goes back to what we had with the radicals, where we didn't ever want a radical in the denominator. We don't ever want an I in the denominator. Excuse me. So here's an example of 3 over 2 plus 4i. Okay, we want to get that I out of the denominator. And when we had square roots like this, if we had, for example, 2 plus the square root of 5 on the bottom, we would multiply by what was called the conjugate. Here, we want to multiply by the complex conjugate. which means exactly the same thing. It's a complex number, so we call it complex conjugate. So for 2 plus 4i, the complex conjugate would be 2 minus 4i. All you do is flip the middle sign. Those are opposites of each other. So for this one, we will rewrite the problem, and then you're going to multiply by 2 minus 4i. 2 minus 4i. Okay. So on the top, we will multiply and distribute. So you have 6 minus 12i divided by then we will FOIL this. So we have 4 and then minus 8i plus 8i. See, the always go to 0. Minus 16i squared. So now we have 4, but remember I squared is negative 1. So minus 16 times negative 1, which is going to be plus 16. So 4 plus 16 is 20. And then to write this in standard form, we are going to divide both the two terms on the top by 20. So this is 6 over 20 minus 12 over 20i. And let's see, 6 over 20 can divide both by 2, so that would be 3/10. And here we can divide both by 4. It's going to be 3/5 I. Okay. Another aspect of this section is figuring out powers of I. So, like we said, I is the square root of negative 1, and I squared is negative 1. So those two things are very important. But how do we figure out things like I to the maybe 24th or something like that? How would we figure that out? And one thing that we would do is we would write it in terms of I squared. So I to the 24th is I squared to the 12th power. Remember that you multiply powers like this. So 2 times 12 is 24, so you get exactly what you wanted. And then I squared is negative 1. So this is negative 1 to the 12th. And since 12 is even, right, then that means that this is going to be positive. So this is 1. So I to the 24th is 1. Now what if we had I to the 35th? Okay, something like this. We still want to write it in terms of I squared. So 2 times what gets you close to 35? So 2 times 17 is 34, right? So then you would multiply by an I to get 35, because you would add this exponent that's right here. So that's I to the 35th. I squared is negative 1. And 17 is odd. So negative 1 to an odd power is going to be negative 1, and then times I. So you get negative I. I kind of like these. I think they're sort of fun. Anyway, I believe that is the last of the complex number section. So make sure that you review this. Email me if you have any questions. I'd be happy to answer them. Google fractals and look them up, and play around with those a little bit. They're pretty fun. All right, have a good day.